Hi, welcome to the Signal Path. I have another product review for you guys today. We're going to take a look at this Analog Arts multi-combination instrument in a box. And this is an oscilloscope, spectrum analyzer, arbitrary waveform generator, as well as a pattern generator and logic analyzer, all built into one unit. And what is also very interesting is that it claims to have some really high-end specs for a very reasonable price when you consider how many things are actually inside this box. And the people from Analog Arts contacted me and they asked me if I was interested in reviewing it. And I said, sure, why not? Send me one and I'll be happy to take a look at it. And first I'm going to show you what different combinations this thing comes in, and then we're going to do this a little bit more like Dave. First we're going to take it apart before we turn it on. And I think it's interesting to take a look at the PCB, and I'm interested in digging out the different data sheets for the parts that are going to be on this PCB. I haven't seen it yet. And then we're going to find out what exactly they do and do a little comparison between the specifications they offer based on versus the components that are actually inside to see how they claim to have such incredible performance coming from this box. So let's take a look at the few combinations this thing actually can be configured. There we go. I hope you can read this. I'm sorry if the writing is small, but I'll have a link there so we can actually directly go to the website and take a look at it. But what is interesting here that I wanted to point out is that these are the different functionalities that you could get from, as I mentioned, oscilloscope all the way down to a pattern generator, and the different model numbers can give you a different combination of these. So the highest end model you can ever get is the SL987, which is supposed to give you a 1 GHz oscilloscope. It's supposed to give you a spectrum analyzer, a data recorder, and a 150 MHz arbitrary waveform generator, a 200 MHz logic analyzer, and a 100 MHz pattern generator. This is a really serious set of configurations, and the oscilloscope is 2 channels, of course, and it has external triggers and so on, and I'll show you that a little bit more closely when we take a look at the unit. But you could also opt out for other units which will have a significant price reduction. This is obviously the most expensive one. That's the one that they have sent me. But you could go, for example, if you only want an oscilloscope, you can just go with the SA series, and it will just be an oscilloscope and a spectrum analyzer. And the spectrum analyzer is essentially an FFT-based spectrum analyzer, so you got to be a little bit careful. It's not a real sweeping spectrum analyzer. It's just essentially the FFT of the signal that you get. But of course, it's the analysis software, so it can make it really easy to look at the different signals. Or you can, if you only want the arbitrary waveform generator and so on, as I mentioned. So, and what about the pricing? Well, the pricing is actually fairly reasonable, based on the specifications themselves. So I have a couple of different prices here. So again, the most expensive unit was the one that I have here, is the SL987. That's $1,260. But if you go on for just this, for just the oscilloscope, you're looking at $720. If you go with the spec, it starts at $195. The $195 is the 100 MHz oscilloscope, and then all the way in different kind of configurations. So there will be a link so you can go ahead and look at their website. So the prices are okay. Again, you have to be, it's very competitive, of course, because once Rigol has released a 4-channel oscilloscope for the price they have, for about just over $400 or so, and it's hard to compete with a USB-based product. But again, if they can meet the specification, it would be pretty good bang for the buck. So let's go ahead and take it apart, take a look at the PCB and how it's designed, because I imagine it's quite difficult to make all these components into one box. Just the shielding itself would be quite challenging. So let's go and analyze the PCB, dig out the datasheet, and see what we have. So here we go, closer look at this. So at the back you have all the digital I/O lines, so you can see, let me get some into point here. You can see all the pattern generator channels and all the actual logic analyzer channels here, and there's a couple of voltages and clocks and so on that go in and out. And what is also a little bit odd is that it doesn't have the right USB connector, at least I don't think, because it should have a device port, not a host port. But anyhow, it doesn't matter so much because they have actually provided a USB cable that has, well, the same end on both sides. A little bit unusual. I'm not sure why they've gone with that. Maybe there's a reason that I can't think of. But either way, anyhow, you have this cable. But normally a USB cable doesn't look like this, as you know. So it will be a little bit difficult to use. But here we go. In the front, you have channel 1, you have channel 2, then you have the trigger, and then you have the arbitrary waveform generator's output and the sync from the arbitrary waveform generator, which can be quite beneficial if you want to take a look at the signal. So you could do some interesting things. If you want to test it by itself, you could take the output of the arbitrary waveform generator, put it into the channel 1, take the sync and put it into the trigger, and kind of self-test itself. Kind of weird and kind of interesting. And so there you go. It seems like it's a very simple construction. Aluminum box, nice and small. And yeah, otherwise I don't see any major problems with it. There is no screw holding the BNCs onto the case, which is, you know, probably should have one, because you can see that these things can wiggle. And eventually I'd imagine that you would run into a problem. But that's a problem that they should be easy to fix by putting a nut here, although the body of the BNCs are actually plastic, so you'll have to have either a plastic screw or maybe avoid over tightening it, otherwise you'll damage the PCB itself, the BNC connector itself. So let's go ahead and take this thing apart. Should be fairly easy. There we go. There's one screw here and one screw here, and I think it's a very simple construction. And there's one other thing I didn't mention. There is also what appears to be a hard drive symbol and a power symbol. I'd imagine this is some kind of a buffer indication and so on. Let me see what we got. Ah, there we go. That wasn't too bad at all. There you go. I see the LEDs already. Oh, it's stuck. Ah, there we go. Let's go ahead and take a close look at this. So what do we have here? We're looking at channel 1 and channel 2 of the oscilloscope, and we have the trigger as well as the arbitrary waveform generator's output and the sink. So this is the order, and you can see, you know, some symmetry here because of the channel 1, channel 2 of the oscilloscope and a bunch of other components there. Now at first glance, one of the very first things I noticed is that there are quite a few mistakes on this board, and I'm a little bit surprised why they have chosen to send me a board with so many corrections on it and not perhaps the next revision of this board. Maybe that was by mistake, but either way, I see so many corrections on it. Let's just, for example, start from here. There is a what appears to be a little bit of a mayhem going on here with different tantalum of ceramic capacitors all connected together. Perhaps they didn't have enough decoupling. Here it appears that some kind of an oscillator or a crystal has been replaced with this component here. There is some other hacked components here together. There is some damage to this BNC connector, perhaps due to some hot air repair that has been done here. And if I go further, again, some more corrections and mistakes here, and you can see perhaps a little bit better if I show you on the side these things. And again, there's just so many mistakes on it that I would imagine that this is not the final revision of the board. I am sure that they have respun this to correct these mistakes. They must have taken forever just to make these changes to this board. And here's again some more damage to this relay here, which I assume is perhaps due to some, either for some calibration or for some attenuation from the input of the oscilloscopes. Again, you can see this damage is most likely due to some hot air soldering and some more little issues here and there. And on the other side of the board, we have somewhat of a similar scenario. We have again a mistake here, some corrections here, replacement there, some corrections here, some hot air damage to this component. So I'm a little bit disappointed by that, and I'm assuming that again that either this is by mistake or that this is not the final revision of the board, and I'm sure that they do not distribute their product this way, because simply making all of these changes on this board by hand individually on each product is completely impractical. And this must have been one of the very, very early versions, so I'm going to give it the benefit of the doubt on that this is something that they have corrected. Now, just by quickly looking at it, I am concerned about a few things. First of all, there is no shield between channel 1 and channel 2. There is no cage around it. And the signals appear to go through a single chip on each side. Now, I suspect that these ICs are dual amplifiers of some kind, and typically these dual amplifiers are used in telecommunication systems on the same die, because in those systems when you have a modem, some kind of crosstalk can be automatically corrected, but in an oscilloscope you have to be very careful because you don't want to have any crosstalk because you're looking at completely independent channels. So I'm a little bit interested to see how they are going to meet the isolation at 1 gigahertz between these two channels. That's very, very difficult to do, especially with these components crammed together. And if anything, just the repair done itself is surely going to cause asymmetries and some kind of a signal coupling problems. And this also is true for the arbitrary waveform generator section. I mean, you have digital domain circuits, highly analog domain circuits, again analog domain circuits here, and digital for the sink and the trigger, and of course again depending on what kind of triggering circuitry they're using, and these have to be very carefully isolated from each other, otherwise you're going to get all kind of problems. I mean, if I turn this on, I shouldn't see the signal in my channel 2 of my oscilloscope. If I put a big signal on channel 1 and a small signal on channel 2, I should see no signal crosstalk between them. And as you have seen with teardowns that I have done on oscilloscopes, and Dave has done oscilloscopes, and he does a very good job also in explaining this, that these type of things are extremely important. And of course, we can see that in RF designs that I have done quite a bit of tutorials and so on as well, that you can see how important something like that would be. So what and quick look here, I can probably tell that there you go, there's an IC here, that's a dual ADC most likely, so the signal will come here to a dual ADC. This is probably some kind of a synthesizer to feed the ADC, because I don't see any other way of feeding this ADC. It's obviously memory. I'm not sure what that is, perhaps something with a trigger, some comparator perhaps. Here we have the DAC. Here's the output driver that drives the DAC. This IC, I'm not 100% sure yet, could be another type of a synthesizer. And what else was I looking at? This guy, I cannot really see the part. Oh, no, this is a Cypress. Okay, this is a USB controller for everything that's down there. At the back, we have some kind of an FPGA or CPLD here. I have to look at the part number more carefully. And again, some more memory. And I'm not sure what that is yet. But again, here's another example that I'm looking at. These traces are supposed to be, according to the specification, 200 megahertz or 100 megahertz. But they're not length matched, and they're also really, really close together. And anyhow, I hope that this can meet its specification. I haven't tried the logic analyzer, so I don't know, but I would be a little bit surprised about the way these traces are. Again, these traces are digital logic. Imagine if you have 16 channels of digital logic coming in and 16 channels of pattern going out. There is noise all over this board. And then right on the other side, you've got your ADC, so it would be difficult to isolate those unless it's done very, very carefully. So let's go ahead and dig out the parts for each of these individual things and see what is used. I'm very curious about the architecture. It looks pretty interesting. It's a nice little board, so let's see what happens. So let's take a quick look at the specification that is provided by this oscilloscope, and I want to share with you a few concerns that I have. So this is an oscilloscope. You should be looking at this column here because we have the 1 gigahertz model. Now, first of all, we have a different bandwidth depending on the vertical spacing that we have from the oscilloscope. Now, normally in a regular oscilloscope, it doesn't matter what your vertical scaling is. You will always get the bandwidth that the oscilloscope is specified at, unless you're using a front-end amplifier in negative feedback, but you change the gain of this amplifier in order to meet different vertical scaling. And then if you do that, because your unity gain bandwidth of the amplifier is fixed, you can actually have a different 3 dB bandwidth as a result of that. And I believe this is probably what's happening here, that at low input signals, when you want to amplify it in order to meet the full scale of the A to D, then your bandwidth drops. So you've got to be a bit more careful. You know, calling it a 1 gigahertz oscilloscope in that case is a little bit stretching it. But anyhow, then they have, of course, 8 bits of vertical resolution. But the other thing that concerns me is here. You can see that the real-time sampling per channel is listed as 125 megahertz. So it's 125 megasample per second per channel. Then the effective is listed as 100 gigahertz. Of course, I'm gonna ignore that because that's most likely just, you know, the software interpolation they do. That doesn't really mean anything in terms of actually resolving signals in the time domain. Now, but if you have 125 megasample per second, you cannot have a 1 gigahertz bandwidth, because if you do, then you're going to fold back all your signal above the Nyquist rate back over and over again into your Nyquist bandwidth. Now, sometimes some oscilloscopes that do subsampling, they can do subsampling of very high bandwidth signals if the signal is periodic, but that requires a coherent clock which is coherent to your signal, your periodic signal, to be fed onto the oscilloscope at the same time, whose frequency you must know before you can do that. Otherwise, you cannot reconstruct your signal. On top of that, you need to have a jitter floor on your clock, on your signal, that has a better floor, much, much better than your signal itself, because your samples have to be extremely precise to be able to reconstruct a signal that has much, much higher bandwidth than your actual sampling rate. This is a common thing they do in subsampling scopes that have very high bandwidth, like the Agilent 80 or 90 gigahertz remote hits. They do this, but you cannot do it in this configuration, there isn't sufficient hardware to support that. On top of that, if you do this and you don't have any anti-aliasing filter, then the signals which fold back become indistinguishable from the signal that are within the Nyquist bandwidth. So you will get a mess of things combined together which you cannot distinguish from one another. So then I became curious about this when I saw this conflicting specification. So I went and I looked at the data sheet of the analog to digital converter, and no surprises there. The analog to digital converter is a Maxim part. It's the Max 19516. It's a dual ADC as we suspected, because both channels are processed by the same IC, and it's a 10-bit part actually, and they're not using all the 10 bits, they're only claiming 8 bits, and it's a 100 megasample per second, so it's likely that they have overclocked it from 100 to 125. Now if you note here, its input bandwidth is indeed it says it's larger than 850 megahertz. So then you may ask yourself, well, why has anyone built an ADC like that? But the reason is because people sometimes want to use the ADC to do down conversion at the same time. That's one of the applications. So what you can do is, instead of using a mixer, if you want to digitize a signal that is sitting at 850 megahertz, is that you can feed it into an analog to digital converter that has a very high input bandwidth. Then the ADC will alias back that signal within its own Nyquist bandwidth, which acts like a mixer essentially, except that the spectrum is folded back and forth, reversed back and forth, depending on which Nyquist band is falling back. Anyhow, but that's a minor detail. Then you can digitize that and then process that. This is a common technique used in wireless systems, up to 2.4 gigahertz or 5 gigahertz or so. People do this all the time. And this is what this was intended for. But you cannot feed a broadband signal from DC to 850 megahertz into this ADC and have it digitized in a traditional sense that you're used to seeing on an oscilloscope. So you're definitely going to run into a problem doing it this way. So I'm curious about actually testing it to find out how this will behave in real life. But what they have done is that they have used front-end amplifiers that do support very high bandwidth. In fact, here's the data sheet of their first amplifier, and as I suspected, it is indeed an op-amp, and that's most likely why its bandwidth depends on the gain that they have set. So here it says triple 1.5 gigahertz op-amp. So there's actually 3 op-amps in there that have a unity gain bandwidth of 1.5 gigahertz, and you can put them in feedback. You can see the feedback path is brought out on 2 different pins, and this is also a common technique so that the layout can become easier on the PCB, and other advantages as well. So you could put feedback network between these 2 ports, and then the gain will change. In fact, here, look here, there's an example right here. Look, the bandwidth is 1650 megahertz if the gain is 1, and the bandwidth is 730 megahertz if the gain is 2. And that makes sense because the unity gain bandwidth is fixed, and the 3D bandwidth therefore will scale with the gain of the circuit. And you can see there's 3 of them. I'm not sure what they're using the third one for, but there you go. That's your 2 channels of your oscilloscope, channel 1 and channel 2. It first enters there. So this does have the bandwidth, but there is no aliasing filter in this in this oscilloscope. So everything gets digitized, and therefore the noise also gets folded back into your spectrum, as well as any signal you may have above your Nyquist, whose frequency will then be unknown because you don't know exactly the ratio of that frequency to your clock frequency. But anyhow, and you don't know which Nyquist band it is landed. There is ways to do that by dithering the clock and jumping between 2 different frequencies, but I don't believe they're doing that. And here's a second stage of the same system. I believe this is the other op-amp they're using. Again, there's 2 of them. This is the package they're using. So they have 2 amplification stages in a row, which would both have would be op-amp based. So they do in fact have a very high input bandwidth, likely close to a gigahertz, like they say, but again, I don't think you can digitize all the way to the end the bandwidth as you would do in a normal oscilloscope. And here you go, there's some more data sheet that actually reflects back on what I was saying. So here you go, the spectrum analyzer, which is also spec to a gigahertz because again it's an FFT-based, but look, the display span can only go up to 60 megahertz, and that makes sense because 60 megahertz is about half of what 125 megasample per second is. This is your Nyquist bandwidth. This is the real digitizing bandwidth. That's why the display span of the spectrum analyzer can only go up to 60 megahertz. And I have a feeling that once we test that, we can actually see signals aliasing back. it can be useful to see a signal. You could look at a spectrum of a narrowband signal that sits close to a gigahertz using this technique, but it will be the alias back signal. You cannot look at a broadband signal in this way. So there you go. This at least confirms what I was saying earlier, and we will go ahead and test that. Other than that, the specifications are fairly nice. You know, they claim a dynamic range of better than 65 dB and a spurious-free dynamic range better than 50 dB. Now, these are the specifications of the ADC itself. Whether the entire system meets these specifications is a different story, and we will have to test that, and we will put some signals to it to make sure that it does. Here we go, some more specification on the arbitrary waveform generator. So again, I have some other concerns, a different set of concerns here. So it has, you know, some 64 kilobytes of memory or kilosamples of memory and so on, 12-bit, which is nice. And now here it says that the sample rate for a sine wave is 400 megahertz, but the sample rate itself is 100 megahertz. That's a little bit unusual. I suspect that they're using two different ICs to generate different types of waveforms. So they're using one type of IC to generate a sine wave and a different IC to generate the arbitrary waveform. So the arbitrary waveform sample rate is actually 100 megahertz, but the sine wave generation is 400 megahertz. So there's a little bit of a difference there. So if you want to generate any arbitrary waveform, you cannot sample it at 400 megahertz. So again, I went ahead and I took out the data sheet for the different parts, and we can take a look and see how that is put together. Here we go. So they're using an analog devices AD9706, which is the 12-bit version of this TX DAC. And this TX DAC is running at 175 megasamples per second, and they're probably undersampling this one at a 100, according to their own data sheet at least. And you can see that this thing has a fairly good performance. It has you know, something close to 80 dB of SFDR up to about 20 or 30 megahertz, which is fairly good. So it's good for generating complex arbitrary waveforms. But obviously the output of this type of DAC cannot go to signals higher than its own Nyquist rate, and it wouldn't be very good close to its Nyquist rate anyway. So I suspect that the bandwidth of the arbitrary waveform generator is limited to probably less than 50 megahertz, and then in order to generate sinusoids, you will have to use a different IC. So I became curious about that, and I found out what the 400 megasample per second was referring to. So they were referring to this IC. This is a DDS, a direct digital synthesizer, and these are used in various applications. In fact, there are two of these on this board. Here's our board. So we have one DDS that is here, that is used to clock the A to D converter. So this is a clock. So I was correct about the fact that this is the clock of the analog to digital converter. And here's another DDS, which is the same as this one. So what I think they're doing is rather interesting and clever. What they're doing is that here's their TX DAC, which is the arbitrary waveform generator's DAC. So this has the low bandwidth output. Here's the last output driver, which drives the BNC output. It has a 50 ohm output driver. And here's the DDS. So when you're generating a sinusoid, the DDS signal is selected and it goes to the output. And when you want to generate arbitrary waveform generator, this memory, this memory is connected here, so you can directly drive data into the arbitrary waveform generator, and then the output then goes through here. So so depending on what you're trying to do, whether it's a pure sinusoid or an ARB, you select the difference between these two, and they should make that a little bit more clear in the data sheet, because it's an interesting architecture, and you know, they should point out exactly what they're doing. And again, don't forget that DDS is nothing more than a digital way of synthesizing any frequency you want. It still does have a DAC at its output, but it's all fully integrated with a very simple DDS core, which generates only sinusoids, and then it has a particular type of interpolator and phase accumulator inside, which runs continuously and uploads the DAC, and it generates a tone, and the tone can be synthesized digitally from a reference and so on. It's not really a PLL, but it's in a sense it synthesizes different frequencies based on a reference frequency. So that's what this chip is. That's what that 400 megasample per second was referring to. That's how they generate different sinusoids. So you should be able to generate high frequency sinusoids with this, but not arbitrary waveforms. So they should make that clear, because it's an interesting architecture, and they should let people know exactly how it works, so you understand your instrument better. and they're using analog devices driver as well for the final output of they're using a single driver. So this is what drives the BNC itself. Again, my concern still remains that these are not isolated from each other, and these things should be in cages and should be really well shielded from each other. Otherwise, if you're trying to use all of the instruments at the same time, surely they will be crosstalk with each other. But nonetheless, it's a fairly complex board and an interesting design. And also, for the sake of completion, let me just show you very briefly the data sheet, the first page of the data sheet of the other components that are in there, just so that you can have a good idea of exactly how it works. Because this way, we're also learning new things aside from just the review of the product itself. So the memories used are both from Cypress. One of them is 1 megabit of memory, and the other one is 8 megabit of memory. And those are the two different memories that you see at the top and the bottom. So this one and this one. And I suspect that this one that's connected to the Xilinx part here is recording and storing the data coming from the oscilloscope. And this one appears to be driving at the DAC itself. So the memory for the DAC is different from the memory and the storage of the oscilloscope. They have broken up that into two of them. And this Xilinx part is not an FPGA, it's actually a CPLD. So it's more of a glue logic that they're using to connect various components together, because all of the communication with the USB and everything is handled through the Cypress high-speed USB controller. So you've seen these type of, I'm sure you've seen these type of parts before. So all the communication essentially is handled by this, because it has a fairly complex internal structure with a whole bunch of different controllers and IOs and I2C controllers and blah blah blah, and everything is built into it. So the CPLD is more of a glue logic connecting perhaps the memory controller, the IOs from the ADC and so on, all the little things you need to do on this board to get everything to work together. And again, here's the CPLD. If you're interested in the part number, is the XC2C256. These are the Cool Runner series from Xilinx, which are very low power consumption. I believe they're implemented in 0.18 micron CMOS, and they claim to have a very good power consumption. This is a reasonably old part. It's from 2007, at least this document version 3.2 was from 2007. Other than that, I don't think there is much else that would be of interest for us, other than now going ahead and turning it on and connecting some signals into it and see what the software looks like. And as I've said before, whenever you're making a USB instrument, your software has to be really good, because that's your only point of interface to this. So let's go ahead, power it on, put some signal into it. So there I've put it back together, and let's do some really basic tests. In order to test the oscilloscope input, because its input is not 50 ohm, what I've done here is I've connected it to a regular 50 ohm line, and here I have a 50 ohm termination in this T junction. So the 50 ohm termination is as close as I can make it to the 1 mega ohm input. This allows me to drive it directly from a 50 ohm source, and this gives it the best chance of having the highest bandwidth that I can to drive it all the way up to 1 gigahertz or so. So I'm going to test the input like this, and the signal itself comes from the Rigol DS G3060 synthesizer. We're going to start at 10 megahertz, and this is a pure tone generator essentially with a fairly good THD. So we can go ahead and try it with that. Unfortunately, what I couldn't get to work is that I couldn't get this instrument to work with my Surface computer. I'm not exactly sure why. It could be because the USB port on the Surface doesn't provide enough power to it, and maybe this thing actually takes more than half an hour. We could try and measure it, but anyway, it doesn't matter too much. It works with my desktop computer, which is what I have connected it to, and now we're going to go ahead and launch the software and see what the software looks like. So let's go ahead and launch the software. There it is, and at the beginning it actually performs some calibration. There we go, and it's running the calibration routine. This calibration routine is intended to cancel any DC offsets or any other kind of imbalance between the gain of the different gain amplitude stages. So because the unit actually does various vertical amplitudes with different op-amp gains, it has to go through the calibration of all those stages, and it does that in a couple of seconds. And then once it is done, you will get another little window, and in that little window you get all of your functions. So here we have oscilloscope, arbitrary waveform generator, logic analyzer, spectrum analyzer, data recorder, and pattern generator. Now, nice thing is that you can launch all of these at the same time, actually, because the unit is capable of operating all of these functionalities at the same time. So let's go ahead and launch the oscilloscope. There we go. And I'm going to launch also the spectrum analyzer, which is the FFT essentially, of the input, and let's put them here side by side. Let me get this set up. There we go. So now they're both side by side here. So our oscilloscope on the left here, you can see that there is a moving point as I move around the mouse, so you can actually get the individual values read out, and same as the spectrum. There's nothing connected at the input, so this spectrum is just simply the noise of the system itself. And you can see that the frequency ends at 51.2 megahertz. That's the highest I believe I can go. So if I enter 55, let me see if that works. There we go, 55 is still okay. I don't remember what the last value is. It seems to allow me, oh no, it says it can only go to 51.2. Okay, so 51.2 was the correct value. Okay, no problem. So 51.2 it is. And here then again, this 51.2 megahertz is limitation because of the A to D's sampling rate, which we knew from what we saw. And this is channel 1 right now. I'm going to go ahead and turn channel 2 on at the same time. And I'm going to put it on times 1 and put this one on times 1. And I'm going to go ahead and enable the input, and let's see what we get. Here's the RF input. There we go. Whoa, it's now very big. So I'm going to, oh, I'm going the wrong way. There you go, 200, 500. I just heard the relay click. Will I be able to view it here? There we go. I'm going to make the timing division smaller, so you can get an idea of how the software works. It's of course right now triggering on channel 1, so I can easily change the triggering on channel 2 and it becomes stable. And I can move the trigger point by moving this point here. So there you go, now I can trigger that. If I move it further out, then of course it becomes untriggered again. So the software is nice, it works reasonably well, it's fairly responsive, and I don't have any problems with the software. And you can here see clearly our tone of interest here, and I can go ahead, for example, let me turn the channel 1 off here. There we go, and it actually turns them off from both of them, so it is not able to turn them off from only one scenario. And I can apply some windowing. I'm going to go with a Hamming window. There it is. So there is our tone. These tones are from the instrument itself. They're not from the synthesizer, because the synthesizer is pretty clean. So you can see that it works fairly well. Now this is not symmetric, and what I noticed is that if I wiggle the input BNC connector, that's what I'm doing. I'm just wiggling the input BNC connector, and this thing moves around a little bit. And I think it's probably because this board has been repaired and it doesn't have a good contact, and that's probably why it's doing that. It does it on the other channel too, and I believe this is just because this board has been repaired many times and so on, and it's not necessarily the design problem. But I guess now it's a little bit more centered. So there you go, you can see the frequency. If I move here, it tells me it's 9.8 megahertz, and it makes sense because here you have in your vertical division 50 nanoseconds per division, which is 10 megahertz. So it's all good. So let's go ahead and increase the frequency and see what actually happens. So we're at 10 megahertz, so I'm going to jump by 10 megahertz at a time, and you can watch it. Here's 10 megahertz, there's 20 megahertz. You see, makes sense again, everything still looks good. So I'm going to go back one division, 20 nanoseconds per division now. Here's 30, 40. We can go back again, 5 nanoseconds per division, and 50. Look, now we are sitting at the very, very edge of the FFT window, and this is the very, very edge that I can go. So if I go any further back, now I'm at 1 nanosecond per division. This is now, you can see the individual quantization levels here. And again, because this doesn't have any filtering, any aliasing filtering, in the digital, analog or digital domain, you're going to see that. So let me go back again on 5 nanoseconds per division, and here's our signal. Now, look, I'm going to go to 60 megahertz, and you should see this guy go backwards. Why? Because now it is gone backwards. The reason is because it's now aliased. So this is a 60 megahertz signal, but the instrument is going to tell you that it's a 40 megahertz signal. Of course, because the instrument has no way of knowing what the input frequency is once it's aliased above it. And this will go on and on. So I'm at 60 megahertz, 70, 80, 90. Oh, the amplitude is now changing. I guess the matching has completely shifted, so the amplitude signal is now grown. That's because of the impedance transformation of the front end of the system itself. This shouldn't be happening in normal situations. There we go. 100, 110. So now we're bouncing back again. So you can see the signal will go up, bounce back, bounce forward, bounce back. So now again, now it's reporting the signal amplitude to be at 7.5 megahertz, but in reality is 110 megahertz. And you can see that this will, of course, also give you the wrong value. And you can continue doing this, and you will always have various levels of aliasing. You can see it will continue to alias, and the signal amplitude will change again because of the impedance of the whole point is continuously changing. So I continue increase the frequency, and it will continue bounce back and forth between the 2 points. And now the harmonic distortion of the signal is getting significantly worse because not only the performance of the analog to digital converter has suffered, but also the performance of the front end has suffered, of the instrument itself. So for any reasonable amount of usage, you don't want to use this beyond its Nyquist frequency, because it's impossible to tell what you're looking at anymore. Right now, this is 37 megahertz. Of course it's not, it's 270 megahertz. You have no way of knowing that because you don't have a precision time-based input to the instrument like a true subsampling system would have. So this is going to continue running into this problem. Well, let's go back to a low frequency that we had, 25 megahertz. So here it's perfectly usable at these points in the frequency. Use it within its own bandwidth, and I don't think you will run into any major problem. I'm not going to go into much further tests other than telling you, the interface is actually quite nice. It's responsive. The software is really small, so it's easily transportable and you can easily install it. And again, it has quite powerful windowing capability. It has everything you would want to have in a regular spectrum analyzer interface. Again, remember this is tied with the FFT to the main oscilloscope window. And now I can go ahead and turn channel 1 on. There we go. And I can reduce the channel 1 amplitude to as small as I can. 5, 2. Remember, there's nothing connected to the input of channel 1. But of course, what you're going to see, as I suspected, you're going to see feed-through between the two channels, and this is because they're not properly shielded with respect to each other. So this is normal to see some of that, and you can see the FFT of channel 1, how closely it resembles the FFT of channel 2. It just has a much smaller amplitude, and the reason again is because it doesn't have proper shielding between the two channels. Other than that, it looks fairly good. Other than that, everything else is good except for everything that I've already gone over. So I have no complaint about the software. You can see it sometimes is a little bit slow to respond, but there's a lot of data going back and forth. And I think if you're going to use it within its specified bandwidth, it looks pretty good. So here's the software for the arbitrary waveform generator, and it can do a whole bunch of different types of outputs, including sine, DC, square, RAM, noise, and different types of modulated signals. I mean, it can do AM modulation, FM modulation, and so on. So it's a fairly capable software, able to generate a whole bunch of different types of signals, which is great because you would want to be able to generate not just functions that you have defined yourself as true arbitrary, but you want also a built-in list of functions, and this does have a fairly good one. Now remember that in order to generate sinusoids above the 50 megahertz range, this thing will actually switch to its DDS, to the direct digital synthesis IC that I showed you. So here I am generating a 100 megahertz signal with an amplitude of 2 volt peak to peak into 50 ohm. I'm connected it to the Keysight oscilloscope, and we're going to take a look at it, and we can see what the quality of the signal looks like, and then we can go ahead and try and generate a square wave, for example, which as soon as you switch to a square wave or ramp or anything like that, you will automatically jump onto generating signals using the actual DAC and not the DDS. So there you go. So now I have it hooked up here. Let's go ahead and take a look at the oscilloscope. And here's our sinusoid. You can see the instrument is measuring at 100 megahertz, which is what it's supposed to be, and its amplitude is 730 millivolt peak to peak. So it's not really 2 volt peak to peak, and it's not really 1 volt peak to peak neither. So I'm a little bit surprised that it is amplitude is so low. Remember, I'm feeding it into 50 ohm, as to be expected, because you have to be able to drive 50 ohm. So I believe the output impedance of the amplifier that they're using is perhaps not exactly correctly defined, and that's why the signal amplitude is different. And I can change the sinusoid from 100 to let's say 200. Oh wait, no, it cannot do 200. I'm sorry. Let's try. I believe 150 should be able to do. There you go. Yeah, it can do 150. There's 150 megahertz, and the output amplitude has further dropped to 434. So this is the upper limit of what it can do. Now I noticed a different problem. So if I go to 10 megahertz, which is the frequency of now it's using the DAC to generate that, and if I go ahead and change the scale, look, there is a DC offset. I don't know why, and I couldn't get rid of it. It's not from the instrument, it's not from the software. It's somehow, that's why it's not triggering, by the way. It's not triggering because the trigger line is here. If I move the trigger, I want to move the trigger line just by itself. There you go. You can see if I obviously put it in there, it will start triggering. So I don't know why the signal has shifted down here. Perhaps again, it's maybe because the unit has been repaired and there is some connection problem there, the solder joint problem. But anyhow, you can see a sinusoid at 10 megahertz, which is what it's supposed to be. Now if I switch to square wave, here's my 10 megahertz square wave, which is reasonable. You know, here's a 10 megahertz square wave. Now if I go to 15 megahertz, then well, it kind of looks like a sinusoid again. It's because it doesn't have enough bandwidth to generate and to maintain all the tones of the square wave. Remember, the square wave is supposed to have odd order harmonics all the way in order for it to look like a square wave in the first place. So if I go to lower frequencies, to 10 megahertz, it will look like a nice square wave. If you go to 1 megahertz, it will again look like a nice square wave. But at higher frequencies, it will break down. So it's the same scenario as before. And let me just generate, for example, something else. Here's a ramp signal. There you go. It's a triangular ramp signal. There you go. So you can do all kind of weird things like that too. But my problem with the unit remains. They have over-specified its performance, and I think it doesn't do it justice. They should just specify it more carefully and more scientifically accurate, because it will be better for their product. You know exactly what the bandwidth is, exactly what the frequency response is, exactly what the output amplitude signal should be. Again, I'm forgiving the fact that there's a DC offset, and I think that's just a default of the unit having been repaired and doesn't have a good soldering on it. If you have a good board, I'm sure this problem wouldn't exist. This is most likely a hardware fault. But I think that if they specify the unit better, it will be a much better represented instrument, and then people can actually rely on data coming from it much more that way. So I was just about to show you the pattern generator functionality, and right now the output is still connected to the AWG, and look, it's sitting at around minus 750 millivolt, and look, as soon as I run the pattern generator software, look what happens. It just jumps up to a different voltage. Now you have to be careful with things like this, because this could damage something, or it could cause a problem if you're not careful with the way it is done. So anyhow, when I launched the pattern generator, I have already closed the AWG. So anyhow, there seemed to be some correlation. Perhaps the software runs some settings and some digital bits gets dumped into the DAC, and that's why you get this. But anyhow, it's a little tweaks like this can make a big difference to improve the product. So here's the software interface for the logic analyzer. I like the way it is because it's very easy to see, and if you're used to those little bit of an old style FPGA simulators, you're going to like this because it behaves in a very similar way. And it works quite well. And again, I'm not going to go into the details because I think there should be another review of this product when some of these issues have been resolved into more detail, because I don't want to just continue going into the really details of this before they have addressed the issues. But one thing I noticed is that you cannot launch the logic analyzer and the pattern generator at the same time. So you can either have one or the other, which is a little bit surprising. At least I could be mistaken, but I can't figure out how to do that, because once I close this one, then I can run the pattern generator, and when I run the pattern generator, then a software which looks very similar comes up, but it's of course different because this is not triggered. This actually has an update hardware button here which will download the bits that you set here and then repeat them onto the pattern generator. So I don't know why you can't launch them at the same time. It's a little bit surprising. I hope this is an implementation that they can provide, because sometimes you want to have both the logic generator and logic analyzer and pattern generator running at the same time, just like you do have the oscilloscope. For example, it actually, I take that back. You cannot run the oscilloscope at the same time neither. So you either have the oscilloscope spectrum analyzer, or the arbitrary waveform generator, or the pattern generators, but not all of them at the same time. Let me just give it a quick try. So here's the oscilloscope. And let me see if I can run the arbitrary waveform generator. There you go. That's good. Okay, so you can at least run these two at the same time. So you can have your oscilloscope and you can run your arbitrary waveform generator at the same time. And of course, you can run your spectrum analyzer at the same time. And then now you have these three functionalities together. But then, no, you cannot run the arbitrary waveform generator or the pattern generator at the same time. So it's either logic or analog, essentially. Now, I'm not sure why. I hope that's not a hardware limitation and that that's something that they can do in the future. Well, there you have it. I think this is one of those products that has quite a bit of potential, but it's not completely finished yet. They have to, of course, have a good revision of the board, do better isolation, update all of their specification, especially the numbers they're reporting for their AWG as well as for their oscilloscope, and they should definitely provide block diagram of how this is connected, because you have to completely understand your test instrument before you can use it. And while it is a really powerful unit, I think they will do themselves quite a bit of justice by redoing some of these things that I suggested throughout this review, and hopefully update that. And I will keep you guys posted if I hear back from them about any changes they plan to make, because I think that they are genuinely interested in producing a good product, and I think we should definitely provide the opportunity and the feedback to help them get there. Well, I hope you enjoyed the review. I didn't want to go again too much detail because I want to have the problems addressed first. Also, I hope you learned some things from showing all the, reviewing all the data sheet of all the components that are on there, looking at the board design, because you can learn quite a lot from when things go wrong as well. And anyhow, so let's go ahead and wait to see what we hear from them. And whenever I do, I will keep you guys posted. Until next time.